One of the big things we're going to need to be able to do is to measure the amount of water that's in a river. And so, in order to do that, we're going to use this term called discharge. And I'm going to give you a definition in two different ways here. So, definition number one, discharge is the volume of water that flows past a given point along a river in a given period of time. So that's like if you stand on a bridge and you watch water flow beneath you and you look at like the volume that passes by in 1 second. But of course, that's going to depend on a lot of different factors, how deep the water is, how fast it's moving. And so we need to be able to measure it and to quantify it. So discharge, we can also define by using a math equation. So discharge is the width of the stream times the depth of the stream times the velocity. Now, the width and the depth are pretty easy to measure. A lot of streams are roughly rectangle shaped, so pretty much anywhere along the width will give you an overall width of the stream. And of course, depth is going to change rapidly over time, which means the discharge can change as well. Now, back to this picture here, this is something that we can measure for a lot of fluids. We tend to measure discharge or the flow rate of volcanoes. We can measure the flow rate of lava coming out of a volcano, which is basically a discharge as well. And you've heard the term discharge when we talked about groundwater. So you can measure the discharge of a spring or of a well in the exact same way. The place where a lot of us maybe hear this is if you've ever installed a shower head in your shower. I've done this a couple of times. And so if you look up the specifications of the different shower heads on the Home Depot website, which is what I did to get this, you can see whichever one I looked up. If you look down kind of a little bit below center over there on the specifications, it says flow rate. So what it says is at the most, this particular shower head has a flow rate of 1.8 gallons per minute. So what that means is if you turned on your shower and put a bucket under it and let the shower run at full blast for exactly 1 minute, when you stop and when you turn it off at the end of that minute, you'll have just a little less than 2 gallons of water in your bucket. And so basically this is, taking the discharge of the shower head. Now, discharge is measured in a lot of different places. The USGS has a website that puts all of the values for measured streams throughout the United States. I always get to it by just Googling USGS real-time water, and it takes me right to it. And so I actually pulled this just today when I'm recording this video. And so if you look at the top right of the screen, there is a map of the United States. Every one of those dots represents a monitoring station along the river. The color tells you how much water is moving through the river. And so the places that are black or blue, or even kind of a teal color, those are rivers that are running pretty high, anywhere between the 76th and greater percentile. What that means is if you look at the value that it had when this was measured last, it's higher than 90% of the measurements along that river throughout history. So that's a lot of water moving through there. And if you remember, there was actually a series of storms that moved through kind of the Midwest and the East Coast just the other day. So it makes sense that those rivers are running kind of high. Now on that map, you can choose whichever state you want to look at. So I also gave you a little shot of just Arizona. You'll notice Arizona doesn't have much running particularly high. And those places that are running a little higher, usually that has to do more with water flow from the dams than anything sort of naturally happening along our rivers. You see there's a lot of white circles. Those are gauges that are no longer in use. A lot of that has to do with lack of funding. So what I ended up doing was clicking on the dot inside of the Grand Canyon. You can see it's green on the map, and that's what the graph is on the left-hand tells us. So it tells us over the last week, you can see that the discharge has been peaks right around 13,000 cubic feet per second. And you see kind of there's a low right around midnight every night as well that gets a little bit lower, somewhere between 10 and 11,000. For the most part, this very regular sort of up and down and day highs and night lows is mainly because of what they do on the dam just upstream. But if we check out the stats for April 14th for this particular gauge, they've been measuring the water levels for 95 years there. So today, when I downloaded it, its most recent value was 12,700 cubic feet per second, which is just a little bit lower than the average or the mean that you see. The very highest it's ever measured on April 14th was in 1942, and the very lowest was in 1963, and that is a very low number. I'm kind of surprised. I'm wondering what they were doing there. It could have been during, I don't know, that's after construction of the dam. I had to go look it up and see what was going on in 1963, but they may have been doing something with the dam at that point too. But anyway, so we can measure the discharge in rivers. Now, if we want to look at kind of rivers all over the world, the largest river is the Amazon. That is based on both drainage area and the average discharge. So if you look, the discharge here is measured in cubic meters per second rather than CFS. Because these numbers are in metric versus our American units there. But the Amazon has an average discharge of 209,000 cubic meters per second. Now, I don't know if numbers help you much, but if you imagine a yoga ball that you fill with water instead of air, that's somewhere around a cubic meter. So you go stand on the banks of the Amazon River and you start counting 1 Mississippi. And in the time it takes you to say 1 Mississippi, in that 1 second, over 200,000 yoga balls go rolling past you. And then you say 2 Mississippi, and another 200,000 go rolling past you. That's a lot of water. But it's a really big river. It has a really big drainage area, which contributes to it too. We actually have to go all the way down to the bottom of this list to get to North America. The St. Lawrence River is up in Canada, so we're going to keep moving from there. Number 15 in the world is our Mississippi River. So we looked at the drainage area earlier. That is just over 3 million 3 million square kilometers an area. And its average discharge is 16,792, which is a tiny, 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 tiny fraction of what the Amazon can carry, which is pretty cool. Now, these parts of this discharge equation stay in balance. So where the other place that, we kind of think about this is in terms of playing with the water hose, right? So discharge is usually given as Q. So in this case, Q discharge is set by how much you turn on the knob at the house to turn your water hose on. If you turn it on a little bit, your discharge is going to be pretty small. If you turn it on bigger, the discharge is going to be higher. But there's a max to it. So let's say for this happy kid here, they turned it on and you have a given discharge. Now, that water doesn't squirt very far. Let's say this little kid wants to be pretty mean and hose off that car right behind him. But his hose won't reach all the way. So what can this little kid do to spray the car behind him if his hose isn't any longer? Hopefully you thought of putting your finger over the end of the water hose, the mouth of the water hose. And we've probably all done this at some point. Now, this is a perfect example of that discharge equation. When you put your finger over the end, what it does is it actually reduces what's called the cross-sectional area. So that width and the depth of the water is now a lot smaller. And we took that down, but the same amount of water still has to get through, so it goes a lot faster. And so the velocity increases when the cross-sectional area decreases, even though Q stays the same. And we can see this happening in other locations too. If you look here in the Colorado River at the 75-mile rapids, you can see where, thanks to that little deposition from the whichever little stream is coming in there, it blocks the river a little bit, makes it a lot more narrow, but you can totally see where those rapids are because the water's moving a whole lot faster.